and its derivatives. And I hope today we shall finish benzene. And then when we finish benzene like this, then we shall go and talk about physical chemistry. Some topic maybe ionic equilibria or physical equilibria and chemical kinetics, depending on the mood. But they are all needed. All those topics, they are all needed, and we should know how. Then, like I told you, when we finish there, then we shall talk about transition elements as far as inorganic chemistry is concerned. So we have been talking about benzene, okay, where we saw the structure of benzene, the Kikude, and then the evidences to disapprove the Kikude structure. It's not disapproving, but to modify the Kikude structure. And then we saw how benzene can be prepared, and all that is important, okay. And then from preparation, talked about the reactions of benzene, where we talked about hydrogenation, so the halogenation, and then sulfonation, nitration, and alkylation, and then hydrogenation. Now, with methylbenzene, the reactions are still the same, okay. However, now with methylbenzene, since the ring, oh, sorry for that, let me just clean and draw something good. Since the ring is bound or has a group that do activates it, a methyl group which activates the ring, okay. This group having a positive inductive effect, it pushes the electrons towards the ring, hence increasing the electron density in the ring, hence increasing the ease of donating electrons towards an electrophile that is joining the ring. Then it becomes more reactive than the real benzene. Not so towards electrophilic substitution reaction. Okay? Yes. However, the incoming electrophile, like what we said, it attaches on para position or on the ortho position. Okay? However, the reaction remains the same. So, for instance, let's start with this and you do the mechanism for us so that you get to use it. Now, I've given you all the science and I want you to do the mechanisms and you get to use it. And I promise we shall do all these 4 mechanisms. So let's start with this. We have our benzene, and like I've told you, the electrophile attaches on the ortho or para position. But now in this case, it's more of a para position. Why? Because the methyl group hinders the incoming electrophile, so that when it is attaching on the carbon 4, it receives less hindrance. So our methylbenzene, and we react it with our chlorine, okay, in presence of a halogen carrier, okay, which is iron 3 chloride. And let me write for you the product, or you write the product and you do the mechanism. It is, we shall get our halogenated, okay, methylbenzene with a chloride, and the chloride, it can attach on the ortho or it can attach on the para position. So can you write the mechanism, please? Hurry up and write the mechanism. Okay, and then this is the CM. So write the mechanism and I'll give you 3 marks for this mechanism. So hurry up guys, let's all hurry up. And yeah, so I've seen all your mechanisms and yeah, you tried. However, those minor mistakes, they can affect you so much. Okay, so let's do this and then we try another one. Okay, yeah. So the first thing that happens, we shall form a halogen. We shall form an electrophile. Okay, from this, whereby the Cl, okay, the Cl2 is going to combine with the iron, this iron 3 chloride. First of all, it has vacant d orbitals and it has a high charge, so that it can polarize the chlorine. It will polarize the lone pairs of electrons on this chlorine, okay, onto itself, and the same effect will be distributed to the other chloride atom, okay, so that in the end you will form a chloride atom, okay, that is partially positive, okay, and then another chloride atom that has been polarized, okay, and this is, I can put here the partially negative, and the negative charge is on the iron. If you are to draw the structure, anyway, that's physical chemistry. Then find the next step is the chloride atom which has been polarized and the one which is electrophilic, it will receive the electrons. What's wrong with this? It will receive the electrons from methyl benzene, and the reaction, by the way, here is super quick, okay, super quick, that you don't even need to, it will be quick compared to the benzene, okay, and then with our partially negative, so whereby this one will donate the electrons, that delocalized electrons on the ring, they will be donated to the Cl, and there are 2 of them. Then this bond completely breaks, okay, and what shall we have? Then we shall have our ring, okay, our ring with a methyl group, okay, and then the delocalized electron. Now you can use dots, it is also okay, to show that this one has lost the electrons, and then you put a plus in between, and this ring, half a ring, points to where the group has been attached. And because here you have the hydrogen, since it is substitution, then the nucleophile that has been generated, okay, with negative charge on the iron, the overall, it will come and take away the hydrogen, okay, the hydrogen, let's do this, and the bond on the hydrogen, maybe let me represent this arrow with a different color, the bond on the hydrogen is taken back inside to delocalize, okay, and in the end we shall form our chloromethyl benzene as our final product, okay, chloromethyl benzene as our final product. So basically it is as simple as this. So this is the mechanism that I wanted, just simple. And the 3 marks, I'll put 1 mark here, I put another mark here, and I put another mark here, and the third for completing the product. Okay? Those are the marks. So let's do sulfonation. Okay, and let me first rub this. So let's now do sulfonation. Oh, and see how we can form benzene sulfonic acid. So in fact you should be doing the mechanism, guys. I know this work is easy. And then let me put the CH3 here, and we shall react it with corn sulfuric acid. Corn sulfuric acid. So what shall we form? Okay, you can complete. You can complete. So the mechanism, yes, I've seen your mechanism, and yeah, some people tried, and yeah, you know. So the sulfuric acid, it is the one that dissociates. Actually, here it dissociates fully to give us the hydroxonium ions or the hydrogen ions. Wilbur. So the hydroxonium ions, and then the hydrogen sulfate ions. Okay, the hydrogen sulfate ions plus the sulfur trioxide, SO3. Okay, now this SO3, this sulfur trioxide, it's the one that is an electrophile. You see, the sulfur, if you are to draw its structure, the sulfur is tetrahedral. Actually, is this a tetrahedron? So the sulfur is bonded to 3 oxygen. Okay, 3 oxygen atoms. This is a trigonal pyramid to form my piece is